Okay, so for today's lesson, we're going to be looking at calculating the enthalpy of a chemical reaction, this time from the bond energies. We've learned in the past that breaking chemical bonds takes energy and is an endothermic reaction, and forming chemical bonds gives off energy and is an exothermic reaction. And these energies, through various types of measurements and calculations, have been measured quite accurately, and therefore we can get a good idea of what the enthalpy of a reaction should be by simply adding up all of the energies needed to break and to make chemical bonds. So again, here we've got this particular statement: the amount of energy required to break 1 mole of bonds between 2 particular atoms. So that, again, is the bond energy. Here we're breaking them. Like I said, that's an endothermic process that takes energy, and the amount of energy released when 1 mole of bonds is formed between 2 atoms, and that is an exothermic process. And like I said, chemists and scientists have determined in fairly good detail how much each of these bonds typically takes to make or break. Here you can see we've got a hydrogen-hydrogen bond, a very well-known bond. Here we've got it to 4 significant digits. Hydrogen-oxygen, here we've got 3 significant digits, perhaps even 2. Here if we take a look at, do we have an oxygen-oxygen? No. Here we've got a double bond oxygen, a lot of energy to break or make that bond. Again, a double bond, C double bond O, a lot more energy than the C single bond O. So that tells us a little bit about the strengths of the bonds. We can make a conclusion stating that that the higher the energy, the stronger the bond is, all right? And the lower the energy, the weaker the bond is, all right? So this is kilojoules per mole of these bonds. And again, the sign isn't placed there because it depends on whether we're breaking bonds or whether we are making bonds. So how are we going to calculate this? Well, this symbol here, we haven't encountered it yet. This is a Greek symbol sigma, and the Greek symbol, sigma, and they used to teach this in mathematics, but this simply means to sum or the sum, and so it means we're going to add up all of the bonds. So if we have the reactant bond energies, and we add them all up, remember that the bond energies that we break, right, is endothermic, and so that means it's a positive value. Now I don't put a positive there at the start of the equation, but we could. That means that these are endothermic processes. It's taking energy to do this. And if we then subtract off, or this negative could be thought of it as being exothermic, all right, that means it's exo. So when we make the bonds, we get our energy back out. And so by taking the sum of the bonds that we have to break, all right, we sum them all up, and we put a plus in front of it because it's endothermic. And then if we add up all the bonds that we have to make, and we put a negative in front of it because it's exothermic, and if we add those 2 things together, we end up with the delta H. We end up with that total amount of energy that was either gained or lost by the chemical reactions. If it takes more energy to break the bonds than it does to make them, then our answer will be positive, and the reaction will be endothermic. And if it takes more energy to break bonds than to make them, then the negative side will be greater, and the answer will be negative, and it will be exothermic. This is another way of writing it, the same thing. N, this simply means the number of bonds, and D simply stands for the bond energies. So this stands for the number of bonds, all right? And the D stands for the bond energy, and that's for that particular type of bond, all right? It might be for a CO bond or a C double bond O bond. It doesn't matter. And this is then, again, the number of bonds formed and the energy formed. Again, there you can see I've got the positive sign. I don't have the positive sign there. We don't write it down normally, but bonds broke is endothermic, and bonds formed is exothermic. So let's do some examples here. Let's say we've got a reaction where we have some water molecules, and I've got this drawn out with a simple, it's not even a Lewis diagram, it doesn't have the dots, it doesn't matter, a simple diagram representing the bonds so that we can see them. And let's total up all of this energy that we're dealing with. All right. So keep in mind, right? Bonds broke. So we're looking at the reactants minus the bonds formed. So what bonds do we have to break here? Well, our delta H, all right, is going to be equal to the number, right, of OH bonds, so OH bonds, times the energy of OH bonds. And you'll notice we only have OH bonds here, okay? And so now it's minus, okay? And this is going to be the sum, and in this case we've got to add up the number of HH bonds times the energy of HH bonds, okay? And we also have the number of O double bond O bonds times the energy of O double bond O bonds, all right? So there are our bonds broken, and there is the sum of all of our bonds formed, and we put a negative in front of it because it is being given off. It's exothermic. So in this case, I've got 1, 2, 3, 4. I've got 4 of those bonds, and the OH bond is 460 kilojoules minus. Now let's sum up all of the bonds formed. I've got 2 bonds, and an HH bond is 436.4. And I've got to add to that the other bond that's formed. And so there's only one, right? One O double bond O bond, and that is 498.7. All right, and that whole thing is in brackets because that's exothermic and we need the negative in front of it. I like to do these things in 2 different steps, keep them separate. So 4 times 460, that is 1840 minus. Now let's do what's in the brackets. 2 times 436.4 plus 1 times, and then that's 498.7 equals, and that gets me 1371.5. So notice, it takes a little more energy to break the bonds than to make the bonds. That means I'm going to have a positive delta H. And let's just do the calculation here. We're subtracting. And it gets me 468.5 kilojoules per mole. And that is the delta H for this entire reaction as stated, as determined by the bond energies. All right? So again, we summed up all of the energies for all of the bonds that were broken, and we subtracted off the sum of all of the energies for the bonds that were formed. In this case, I had more energy in than I got out, which means we have a positive delta H. This is an endothermic reaction. This is an endo reaction. All right? Let's do another example here. Okay, let's look at this one. Now, we haven't gone over how to draw Lewis diagrams officially in this course, but you would have done it in terms of preparation for your grade 11 review test. So CH4, it's not too crazy to remember that we're going to have some single bonds here. And so we're going to have to draw some rudimentary pictures here. O2, again, to keep the bonding, that's not completely out of whack there either. Again, CO2, I believe we have the ability to figure out some of these basic structures. And then again, we've got 2 of these H2Os, HOH, and an HOH. Once you have your structures, we're ready to go. Delta H, in this case, it is going to be, actually, yeah, we'll write down the whole equation. N, CH, D, CH, plus N, O, O, D, O, O. And now to the products, minus And here we've got NCO, DCO, and NOH, DOH. All right, I think we've got all of our bonds. Now we're ready to fill it in. For CH is 414. O, there's 1, and it is 498.7. C double bond O, down at the bottom. It's a big one. Two of those bonds. 745. And NOH, what's OH? OH, 460. They're single bonds. And again, we've got 4 of them. 4, and that's 460. All right, 1, 2, 3, 4. Beautiful. Again, I like to do them as bonds broke and bonds made separately. 4 times 414 plus 498.7 equals 2,154.7 minus 2 times 745 plus 4 times 460 equals 3330. Notice in this case, more energy from the bonds formed than from the bonds made. That means we're going to get a negative number, and that is going to be minus equals. So we end up with negative 1175.3, and again, kilojoules per mole. This guy, we had more energy given off by the bonds formed, so the negative is greater than the positive. This is an exo reaction. All right? Okay? So, this was a very short lesson, very straightforward. There are some practice problems you can do, and you also have plenty other practice problems and things from previous classes that you can continue to work on at this point in time. Okay.